This is section 1.5, where we look at linear first-order differential equations and an application of mixture problems. If you recall, when we used separation of variables, what we had to do was modify algebraically by multiplying and or dividing by an appropriate factor so that the variables were separated and we could integrate directly. For example, if we look at dy dx, we had actually solved this problem equaling 3x squared y. We multiplied both sides by 1 over y. We probably thought about it as division, but in any event, we did obtain 1 over y times dy dx equaling 3x squared, which, if you expressed it in differential form, then we differentiate, we're able to integrate both sides. But the point here is that this equation, after modifying, can be recognized as the derivative of, with respect to x, of the natural log of y on the left-hand side, because the derivative of the natural log of y is 1 over y times its the derivative of y, dy dx, and then the derivative with respect to x of x cubed on the right-hand side, because the derivative of x cubed, of course, is 3x squared. So we refer to that factor as the integrating factor, and we formally define it. Now this Greek letter here is rho, lowercase rho, and that's how I make my rows. And we define that to be the integrating factor. Could be a function of both x and y, and it's the factor that when we multiply both sides by a differential equation gives us something we can integrate, or in other words, both sides are recognizable as derivatives. So we now look at the general first-order linear differential equation, and we say that it's non-homogeneous or homogeneous or non-separable if it has this form, where we have dy dx isolated and then plus a function of x times y equaling some other function of x. And the integrating factor is given to be, it's just a function of x, so it's rho of x, and it's e to the integral of p of x with respect to x. And so that, when it is in this standard form for a first order dy dx, first order linear differential equation, the coefficient of y, whatever that function of x is, represents p of x, and the integrating factor is e to the integral of that with respect to x. So the integrating factor actually has a very special property, and it's such that its derivative is itself multiplied by the function we are integrating. For example, if we have that rho of x is defined to be e to the integral of p of x with respect to x, and we want to find rho prime, its derivative, then we would use the formula for e to the u, and the formula for e to the u, recall of course, is just simply e to the u times the derivative of the power on the base of e du dx. So this would be e to the integral of p of x with respect to x, but then times the derivative of that power. And so we can indicate that as the derivative with respect to x, so we use our differential operator, of the integral of p of x with respect to x, the power. But then we have e to the integral of p of x with respect to x, but then the derivative with respect to x of the integral of this function with respect to x Well, the derivative undoes the integration. So the derivative of the integral of something is just something. So that's p of x. And so that shows us the special property that the derivative of the integrating factor is itself e to the integral of p of x with respect to x times the function that we are integrating, p of x. So here's a little cookbook recipe, a method to solve differential equations of this. Again, this is our standard form. Have to make sure it's in that standard form before we do anything. First, just find the integrating factor, and then multiply both sides of the differential equation by it. And the left-hand side will always be the derivative of the product of that integrating factor and the function y. So we could express it using either the differential operator uppercase D with a subscript of x, or we could just use the differential operator D to mean the derivative of this product. But notice it's the product of the integrating factor rho of x and the function y. And then we're going to integrate and solve for y and obtain the explicit general solution. Now here's the reason why it works. If you start with in general, you don't really have to worry about the proof of this, but I think it's important to see, as well as important to have a full understanding of what's happening mathematically. If we take rho of x, the integrating factor, which is again e to the integral of p of x with respect to x, and we multiply through, we get e to the integral of p of x with respect to x times dy dx, and then plus e to the integral of p of x with respect to x times p of x times y, equaling e to the integral of p of x with respect to x times q of x. And on the left-hand side, at this point, we can recognize that e to the integral of p of x with respect to x is again rho of x. So I'm going to replace this by rho of x, but notice that e to the integral of p of x with respect to x times p of x is actually rho prime of x, which we had proven up here. So we had proven that, remember the special property that the integrating factor has. Its derivative is itself times p of x. So that's what we have here, so that's rho prime of x. So therefore what we have is rho of x dy dx plus rho prime of x times y equaling, and the left-hand side we're really not majorly concerned about, because notice that that's going to be in an integral that's entirely a function of x, because you have e to some power that involves x times q of x. And so whatever that is, hopefully it's not going to be too challenging, but we will be able to integrate it. But the point here is that the left-hand side is now the product. We could express it as the product or the derivative of rho of x times y. Because if you think of the derivative of a product, you have the first factor, p of x, derivative of the second, dy dx, but then plus the second factor, y, and then times the derivative of the first, and the derivative of rho of x is rho prime of x. And then we have the right-hand side, which again we know we'll be able to integrate. Okay, so that's the reason why it works, and it proves to us that the left-hand side can always be expressed as the product of rho of x, the derivative of the rho of x times y. So some examples. Now you could follow the cookbook recipe if you like. Here's, you want the explicit, general, and particular solutions. So the first step, make sure it's in standard form, and it is. Now, textbook uses prime notation with these examples, so that's why I used it here. So the dy dx plus p of xy equaling q of x, which is our standard form, is the same as saying y prime plus p of xy is q of x. So note that in this example it is in standard form, and that p of x is the coefficient of y, in this case just the constant, -2. So the integrating factor, rho, so I'm just going to call it rho. You can call it rho of x if you like, but I'm just going to choose to call it rho. Is equal to e to the integral of p of x with respect to x, but again p of x is the -2, so e to the integral of -2 with respect to x, or just e to the -2x. Now we don't add a constant of integration here, and it can be argued easily that even if you did, you'd be able to prove the same result, but it's not necessary to add a constant of integration to the integrating factor. So we just get e to the -2x. Alright, now we're going to multiply. So everything gets multiplied by e to the -2x, so e to the -2xy minus 2, I'll slide the e to the -2x in there. I'm sorry, that's e to the -2xy prime, and then I'll minus 2 e to the -2xy equaling 3 times e to the 2x. And just throw this aside. Should be able to do this mentally. We're taking 3 e to the 2x and we're multiplying it by e to the -2x. So that's 3 e to the 0, or just simply 3. Okay, so now the left-hand side we know is expressible as the derivative of the product of the integrating factor, e to the -2x, and y. Now there's a couple things I want to mention here, and that's going to be equal to 3. You should double check this. And the way to realize, although we've proven it, another way to realize what this product is to just simply look at the term containing the derivative and take away its derivativeness. So if you look at the term containing the prime, e to the -2xy prime, the factor that's going, the product that's going to be the derivative of the product that's going to give us this left-hand side will be that term taking away the primeness. Okay, so even though we proved, another way to think of it is just the integrating factor times y, as we've proven. Now, at the same time, we should check that this is true. What is the derivative of this product? Well, here's the first factor, e to the -2x. Derivative of the second, there's y prime, plus the second factor, y, there it is. And then the derivative of the first, and the derivative of e to the -2x is e to the -2x times the derivative of the power negative 2x, its derivative is this negative 2. Okay? Alright, so once that's finished, we can integrate. Now, you could throw the integration symbol in front of each side if you wanted to. If you do, make sure you include the differential dx on the right. But then on the left, the integral of the derivative of something, integration is anti-differentiation. So the integral of the derivative of this quantity is just that quantity. So we get e to the negative 2xy equaling, then we integrate 3x, or we integrate 3 with respect to x, and we get 3x, and there's where we add our constant of integration. And now to solve for y, we could divide by e to the negative 2x, and so you could think of dividing both sides by e to the negative 2x literally. And that'll give us y. And one way to express this is as the quantity 3x plus c, but then times, let's bring this e to the negative 2x up to the numerator as e to the 2x. And that's going to be our general solution. Right, now if we want the particular solution, we use the initial condition. Let me just separate this. And the initial condition was that y of 0 is 1, meaning that when x is 0, y is 1. So therefore, into the general solution, we have that 1 is equal to c, because if we put a 0 in for x, 3x is gone, and then e to the 0 is 1, so we just get 1 is c. And then the particular solution would be y equals the binomial quantity 3x plus 1 now times e to the 2x. And that's the particular solution. Okay, so some more examples. This one requires us to obtain standard form by dividing everything by x. So we get y prime plus 5 over xy equals 7x. The integrating factor rho, let's do it here. Rho is, again, the integral, e to the integral of p of x with respect to x. So e to the integral of 5 over x with respect to x. Now if you want to factor out the 5, you can. But then the integral of 1 over x with respect to x is the natural log. So e to the 5 natural log of x. And then what we could do is use our power property for logs, bring this coefficient up to be the exponent on the argument. So e to the natural log of x to the 5th. And then use our inverse property that e to the natural log of something is that something. So we get x to the 5th for our integrating factor. And this thing happens quite often where it turns into a natural log and then we got to use the power property for logs in reversed. Recall I'll write it with natural logs. Let's say natural log of m to the p power is p natural log m. So we use that property in reverse here, from this step to this step. And then again the inverse property. Okay, so now we're ready to multiply. So we multiply everything by x to the fifth. So x to the fifth y prime plus, this gives us 5x to the fourth, because one factor of x cancels, times y equals 7x to the sixth. So make sure you multiply the right hand side by the integrating factor as well. And then the derivative, at that point the left side is the derivative of a product. And remember, that's the integrating factor, x to the fifth, times the function y itself. A couple ways again to double check. Look at the term to know what this product is, look at the term containing the derivative, and take away its derivativeness. So x to the fifth y. Or, as we've proven, the integrating factor times y. And to double check, think of the product rule. First factor x to the fifth, derivative of the second, y prime, plus second factor y, derivative of the first, 5x to the fourth. And that equals 7x to the sixth. So great. You could skip the step of showing the integration. But if you do formally, we should include the differential dx on the right. And the integral of the derivative of something is just the something. So we get x to the fifth y on the left is equal to, look at this, works out pretty, 7x to the seventh over 7, or x to the seventh, add our constant. We'll divide everything by x to the fifth to solve for y. And so we get that y is equal to, becomes x squared plus, I'm going to leave it as c over x to the fifth. And that again is our general solution. For the particular solution, the initial condition was that y of 2 is 5, which means when x is 2, y is 5, so into the general solution, 5 is equal to x is 2. So 2 squared plus c over 2 to the fifth. So we get 5 equals 4 plus c over 32. So then 1 equals c over 32, and c is 32. And so therefore, into the general solution, we get the particular solution, x squared plus 32 over x to the fifth. And that's our particular solution. Okay, continuing, we again see an example that requires us to fit the standard form first by dividing everything by 3x. So we get y prime plus 1 over 3x times y equaling 4. And now the integrating factor. So again, rho is equal to e to the integral of p of x with respect to x. So that's e to the integral of 1 over 3x with respect to x. Here, in order to see it, might be advantageous to factor out the 3 that's in the denominator as 1/3. And then we have the integral of 1 over x with respect to x. Okay, which is the natural log again. So e to the 1/3 natural log x. Use the power property in reverse. E to the natural log of x to the 1/3. And then finally the inverse property. And we get x to the 1/3. So at that point we multiply. Okay, and you always multiply by the equation that was in standard form. So x to the 1/3 y prime. Okay, now x to the 1/3 times 1 over 3x would be 1/3 x to the it would be 1 over 3 x to the 2/3. Because if we're multiplying by x to the 1/3, this is an exponent of 1 in the denominator, canceling 1/3 of a factor of x, we're left with 2/3 in the denominator. And then times y equals, and again make sure you multiply the right hand side as well by that integrating factor of x to the 1/3 in this case. Okay, now we know the derivative of the product, x to the 1/3 y. You could verify that again. Here's the first factor, x to the 1/3, that is. Looks like I wrote a 2 there, but it's a 3. First factor, derivative of the second y prime, plus second factor y, derivative of the first, derivative of x to the 1/3, 1/3 x to the negative 2/3. There's the 1/3, and the x to the negative 2/3 shifted to the denominator makes x to the 2/3. And so that's equal to 4x to the 1/3. Again, optional step showing the integration symbol. And integrating the derivative of something, we get the something. So x to the 1/3 y equals, okay, and then integrating 4x to the 1/3, we get 4, I'll just do it right here on scrap paper. We get 4 times x to the power 1 greater is 4/3 divided by 4/3, latter constant, but then inverting this denominator and multiplying, that's 4 times 3/4 x to the 4/3. So we just get 3x to the 4/3. And then plus the constant of integration. And then at that point, to get the general solution, we'll divide everything by x to the 1/3. And we have y is equal to, okay, this would just give us 3x, because when dividing common bases, we subtract the exponents, and 4/3 minus 1/3 is 3/3 or 1. And then I'm going to leave it as plus c over x to the 1/3. So this is our general solution. And for the particular solution, use the initial condition that y of 1 is 4. So into the general solution, y is 4, 1x is 1. So 4 is 3 times 1 plus c over 1 to the 1/3. So 4 equals 3 plus c. So it looks like c is 1. And then for our particular solution, y would be 3x plus 1 over x to the 1/3. So that's our particular solution. Alright, I'd like to finish up this last one on this video. And then we'll look at the mixture problems in the next part. So this is already in standard form. So we can go immediately to calculating the integrating factor rho, which again is e to the integral of p of x with respect to x. So e to the integral of p of x in this case is 2x, the coefficient of the y. So that'd be e to the integrating 2x, we get x squared over 2x squared over 2, or just x squared. And so it looks like that's it. That's our integrating factor. And so we multiply. So e to the x squared y prime. I'm going to slide the e to the x squared in after the 2x in the second term there. So 2x e to the x squared y equaling, and then on the right, x e to the x squared. Okay, the left-hand side again is the derivative of the product. In this case, the integrating factor e to the x squared times y. Again, you should verify that that's true. I always do. Here's the first factor, e to the x squared, derivative of the second, y prime, plus the second factor, y, derivative of the first, and derivative of e to the x squared is e to the x squared, but then times the derivative of the power on the base of e, and the derivative of x squared is this 2x. So, verified that. And recopy the right-hand side. Throw the integral symbol in front of each side here. Again, make sure it is good practice, I suppose. It helps you think about the integral on the right. So now for the left-hand side, the integral of the derivative of this quantity is just that quantity. So e to the x squared y equals, okay, here you have to be a little bit careful. Let me do it aside. Show this integration, x e to the x squared. Remember when we have a product of exponentials and algebraics, the exponentials dominate. So here we're going to try to fit e to the u by taking u to be x squared. The du is then 2x dx, and modifying we get 1/2 du is x dx. So the x dx then makes up 1/2 du. And so to fit the basic formula, bring out the 1/2 integral of e to the u with respect to u, which is 1/2 e to the u plus our constant, so 1/2 e to the x squared plus the constant. Okay, so you have to be a little bit careful with the integrations. If you could do that mentally, that's great, knowing, just mentally that you need the 1/2 as a factor in there. So 1/2 e to the x squared plus or constant. A lot of times you want to do those types of integrations that they're a little bit involved. Do them on scrap paper or off to the side rather than to clutter the process. Okay, and then we're going to solve for y by dividing by e to the x squared. So we'll just divide everything by e to the x squared. And so then we get that y is equal to, this would just be 1/2, and then plus c over e to the x squared, and that could be our general solution. For the particular, the initial conditions, y of 0 is -2. So into the general solution, -2 is 1/2 plus c over e to the, that'd be 0 squared, which is 0. So that gives us -5/2 equals c. And so then y is 1/2, c is -5/2, so -5 over 2 e to the x squared. I suppose you could write that as 5 over 2 times e to the -x squared would be equivalent, and that's our particular solution. Okay, so we'll come back for a second part and talk about mixture problems.